Hello and welcome to this video. In this video, we are going to solve the first 6 exercises of chapter 1. So let us start with exercise 1. We have n real numbers and we have to show a double inequality. Okay, so let us first prove the first one. The first one is just a consequence of Cauchy-Schwarz. Okay, so recall that Cauchy-Schwarz inequality can be written in this way. And now take in particular AK equal 1 and BK equal XK. What happens? Okay, so actually I just need to raise to the power 2 first because I have a square here. So, okay, so this is first form, second form, okay? So in the second form, take AK equal 1 and BK equal XK. What happens? Just replace. So we get sum of XK squared less than sum of 1 squared times sum of XK squared. Now, this is just a sum of ones, so 1 plus 1 plus 1 n times. So this is just n. And that's it. This is the first inequality. Okay, the second inequality, okay, consider the first form of Cauchy-Schwarz. Okay. And take now, again, AK equal 1, but BK equal XK squared. Right? So we get sum of XK squared, right? This one. And this one is sum of 1 squared. Which is what? Which is actually n squared to the power 1/2. So n to the power 1/2. Okay? And that's it. If we multiply this by n, we get n to the power 3/2. And that's it. This is just the second inequality. Okay? So this is an easy consequence of Cauchy-Schwarz. So this concludes exercise 1. Exercise 2, also a consequence of Cauchy-Schwarz. We have now positive real numbers, x1, xn, whose sum is equal to 1. We have to show this inequality. Okay, and we have to show that equality holds for certain values of the xk's. Okay, so two things. Let us first start with proving the inequality. So again, consider the Cauchy-Schwarz second form. And take now, it's a little bit tricky actually. So take AK equal radical xk. We can do that because xk is positive. And bk equal 1 over radical xk. So so AK bk is 1 here. Okay? And AK squared is xk, bk squared is 1 over xk. Right? So we get this inequality. And now this is once again n squared. And this is equal to 1 by assumption. So I get what? I get n squared is less than sum of 1 over xk. Okay, this is the inequality. Now, when do we have equality? It's not difficult. Just take all xk to be the same 1 over n. Then, of course, these are positive numbers and they sum to 1. And the sum of the inverses is the sum of n, because 1 over xk equal n. And this is just n squared. So equality is achieved for certain values of xk. Okay, so this concludes exercise 2. Exercise 3, show that if A is not empty and bounded from above, yeah, we should include the condition that it's not empty in order for the sup to exist. Okay? So not empty and bounded from above. So the sup exists, but we have to prove that the sup of A is in A bar. Now, the sup of A need not be in A, because the sup need not be a maximum. If the supremum is a maximum, then of course it belongs to A. But it's not far from A. It's really glued to A. It's in A bar. Okay, and same thing for the infinium. Okay, so we have to use proposition 1.6. Okay, by proposition 1.6, I have a characterization of the points which belong to A bar. A point belongs to A bar if every neighborhood of that point meets A. right? Or equivalently, we have to prove that sup A minus epsilon, sup A plus epsilon meets A. So there's a point here in A, in this interval. Okay, but we will prove more actually. If epsilon is positive, we know by a characterization of the sup that there exists x in A which is bigger than sup A minus epsilon. And this is, I hope you remember, this is not difficult to prove because I'm saying what? What is the supremum? It's the smallest lower bound. So sup A minus epsilon is strictly smaller than sup A. So it's not an upper bound. So I don't have for every x is less or equal. So the negation is that there exists x which is bigger than sup A minus epsilon. Okay. So I'm just using the fact that sup A is the smallest upper bound. So anything smaller is not an upper bound. Okay. So actually, and of course, since x is in A, it's less or equal than the supremum of A. So actually, there exists a point x in A which is between sup A minus epsilon and sup A. And therefore, it's also between sup A minus epsilon and sup A plus epsilon. Okay? So x is in the intersection of this neighborhood of sup A with A. So the intersection is not empty. And by proposition 1.6, sup A belongs to A bar. And the proof for infinium is completely similar. Inf A is the biggest lower bound or the greatest lower bound. So anything greater is not a lower bound. So I can find x in A strictly less than inf A plus epsilon. And of course, since x is in A, it's bigger than inf A. So I can find x in this interval, inf A plus epsilon. And therefore, x belongs to this intersection. Okay, of course, this intersection is contained in this bigger set. So this intersection here is not empty. And therefore, also by proposition 1.6, inf A belongs to A bar. Okay, and now we can conclude what? We can conclude that if A is closed, then the supremum is actually a maximum because it belongs to A. Okay, so the sup is a max only if it belongs to the set. Okay, so this concludes exercise 3. Exercise 4, also an application of proposition 1.6 or the corollary of it. We consider a set, the set A, which is just the sequence of the powers of radical 2 minus 1. So I start with radical 2 minus 1, radical 2 minus 1 squared, cube, etc. Okay, first you have to show that radical 2 minus 1 to the n is less than 1 over n. And this is an easy exercise of mathematical induction that, so in principle, you can prove these such kind of things by induction already in school. So let us start with, okay, first of all, why is it, we have a double inequality here. Now, the first inequality is easy because radical 2 minus 1 is positive, so all powers are positive. Okay, so this is not a big deal. So we just have to concentrate on this inequality. So so what do we have to do if we want to use induction or recurrence, principe de récurrence? For n equal 1, what happens actually? For n equal 1, the statement reads radical 2 minus 1 is less than 1 over 1. And of course, this is true because the radical 2 is less than 2. So the statement is true, the proposition is true for n equal 1. But I have to notice actually that this is not I can do a better estimate here actually. I can put here radical 2 is less than 3/2, not only less than 2, because radical 2 is about 1.4. So actually radical 2 is less than 3/2. So when I subtract 1, I get radical 2 minus 1 is less than 1/2, which is a better estimate than this one. And why do I need this actually in the second step? So now suppose that the statement is true for some n. I want to prove it for n plus 1. So I write radical 2 minus 1 to the power n plus 1 as radical 2 minus 1 times radical 2 minus 1 to the n. So I split it into 2. Now by my first observation, this factor here is less than 1/2. And by the induction assumption, this second factor is less than 1 over n. So the product is less than 1 over 2n. And now this is less than 1 over n plus 1. Why? Because n is bigger or equal than 1. So since n is bigger or equal than 1, I add n, I get 2n bigger than n plus 1. I take the inverse because both are positives. So I get 1 over 2n is less or equal than 1 over n plus 1. And therefore, I get the statement for n plus 1. So if it's true for n, then it's true for n plus 1. Since it's true for n equal 1, it's true for every n. So by the principle of mathematical induction, I have this. Okay. Now, this inequality is just an exercise in mathematical induction, but is not really required in the proof of the second part. I can deduce B from A, of course. Why? Because the first inequality tells me that, in particular, radical 2 minus 1 to the n tends to 0 as n tends to infinity. Okay? So 0 is actually in A bar by proposition 1.6 because it's a limit of a sequence in A. Okay? Now, I don't really need this estimate to show 2 because I know that radical 2 minus 1 is less than 1. So it's positive, it's between 0 and 1. So when I raise to the power n, it tends to 0 actually because, okay. But this is a precise estimate. Okay, it tells me that this sequence tends to 0, but faster than 1 over n. Actually, it's much faster because this is a geometric. We have a geometric convergence here, not just 1 over n. So this tends to 0 much quicker than 1 over n. Okay, anyway, so 0 is the limit of the sequence, and this sequence in A, so 0 is in A bar. Okay, and it's not in A. So in particular, A is not closed. Okay, fifth exercise. Consider the set 1, 1/2, 1/3, 1 over 4. We have to show that this set is not closed. Actually, for the same reason, we already know now why. But if you add 0, we get a closed set. Actually, okay? We have to find what is A bar. So we'll prove that A bar is actually this set. Okay. So of course it's not closed because this A is just a set of, is a sequence actually. So the sequence 1 over n is a sequence in A and it converges to 0. But 0 is not in A, it's in A bar. So A is not closed. Oh, so this is not difficult. Now, to show that A bar is equal to this one, we have to show first that this set is closed. Okay? So I call the set B. So B is just obtained by adding to A 0. So I claim that B is closed. Okay, how do I know that B is closed? There are several ways to prove that. I will give you one of them. Look at the complement. If the complement is open, then B is closed by definition. Now, what is the complement of B? I can write it as a union of an infinite number of open intervals. It's the union of minus infinity 0, 1 infinity, and all these intervals. Okay, how do I prove that? Double inclusion. Okay, so let us prove that this set on the right is contained in this set. So I take an element in this set on the right and prove that it's not in B. Okay, fine. So X is in this union here. So it's either here or here or here, in some one of them. If X is here, then X is strictly negative. It cannot be in A, because A actually is contained between 0 and 1. So if X is negative or bigger than 1, then X cannot be in A. And of course, it's not 0, so it's not in B. Okay? So if X is here or here, it's not in B. So there remains the possibility that X is here. If X is in the union, then X is in one of these intervals. So there exists one integer m such that X is between 1 over m plus 1 and 1 over m. Okay? Now, there are no elements in capital A inside this interval. Okay? Because the other elements of A are either, so 1 over k is either on the right or on the left. Between these two inverses, between 1 over m plus 1 and 1 over m, there are no elements in A. So it means in particular that X is not in A. Okay. And of course, since X is bigger than 1 over n plus 1, it's strictly positive, so it cannot be 0. So I have two information now. X is not in A. If X is here, then X is not in A, and X is not in 0, so it's not in B. So if X is here, then X is in the complement of B, cannot be in B. So this is the first part. This horrible set is contained in the complement of B. Okay, so this is half of the equality. Now I have to prove that I have to take an element here, so the reverse inclusion. I have to take an element here and prove that it's here. Okay, so now I take X in the complement of B. Okay, if it happens that X is negative, then fine, we are here. If X is bigger than 1, it's here. So I assume that X is between 0 and 1. Okay, but if X is not in B, then X is different from 0 because 0 is in B, and X is different from 1 because 1 belongs to A. So X now, if it's not negative and not positive, not bigger than 1, then it's strictly contained between 0 and 1. So 1 over X is bigger than 1. And now I take M to be the floor function of 1 over X, which is now an integer bigger or equal than 1. Okay? So what do I have? I have M by definition of the floor function. 1 over X is between M and n plus 1. But of course, since X is not in B, then X is different from 1 over M for, okay? So the inequality here is strict, actually. Yeah, right? So if 1 over X is between M and n plus 1, then X is between 1 over M plus 1 and 1 over M. But it cannot be equal to 1 over M because X is not in A, because it's not in B. So I have a strict inequality here. And therefore what? Therefore X is in the union. So what did I prove now? I proved a double inclusion. First, I took X here and proved that it's here. And then the second step, I took X here and proved that it's here. Okay, so what is the conclusion now? If I look at the form of this union here, all the intervals here are open. Open, union, a union of open. But we know that any union of open set is an open set. So the complement of B is an open set. Therefore, B is closed. Okay. And okay, now I have to conclude. B is a closed set containing A, right? But A bar is the smallest closed set containing A. Therefore, A bar is contained in B. But A bar contains A. So A bar is a set between A and B. But B differs from A just by 1 point. So I have just two possibilities. So A bar is either A or A union 0, which is B. Okay? But since A is not closed, this possibility, I cannot have this case. So I have to conclude that A bar is precisely B, which is A union 0. Okay? So this concludes exercise 5. And now, the last exercise. We have to find the interior, the closure, and the boundary of these 5 sets. Let us start with the integers. Actually, we proved in the lectures that n is closed, right? But let us first determine the interior. No interval, no non-empty interval can be contained in n because any interval, any open interval of the form n minus epsilon and n plus epsilon contains irrational numbers. So cannot be contained totally in n, right? So it's not included in n. So what this means is that n cannot contain any open interval. Therefore, the only open set which is contained in n is the empty set. Therefore, the biggest such open set is the empty set. So the interior of n is empty. I think we gave this in the lectures, okay, but we are repeating here. So, all right. Okay, now to determine the closure, I claim that actually we know that n is closed, but why? Let me give you 3 proofs of that, and you choose the one that you understand better. But you already know that n is closed actually. So first way, as we did in the previous exercise, we write the complement of n as the union of open intervals. So if a real number is not a natural integer, it's either negative or positive. If it's negative, it's here. If it's positive, we know that every real number is between two consecutive integers. But since it's not an integer, the set here is open. Okay, so this is not difficult to prove, and I think we already made this observation in the lectures. So conclusion: R without n is a union of open intervals, and therefore it's an open set, and therefore n is closed. If n is closed, it's equal to its own closure, right? So the closure is n, of n is n. Okay, second way, double inclusion, right? So I first take x here. Okay, sorry. I want to prove that this is open. How do I know that? I go back to the definition. Okay, so take x in the complement of n and of the integers, and take n to be the floor function of x. Then x is between n and n plus 1, and it cannot be equal to n because it's not an integer. So I have a strict inequality here. And now we do as we did in the lectures. I take the distance between x and the boundary of the interval. So I take the minimum between x minus n and n plus 1 minus x. Okay, so r is less than these two numbers. And then, as we did in the lectures, the interval x minus r, x plus r is contained in this bigger interval. Okay, we did that in the lectures. So what did we prove? We proved that if x then the complement of n, then there is a whole neighborhood of x contains in R without n. So this proves that R without n is open by definition of an open set. Okay, so this is the same thing. So if this is open, then n is closed, and therefore n bar equal n. So same conclusion. Okay, there is a third way to prove that n is closed by using proposition 1.6. Okay, if you already understood these two ways, you can skip the third way, but otherwise I will give it. To prove that a set is closed, we have to prove that the closure of the set is contained in the set. So I take x in the closure of n. This is just the integers n. Okay. If x is in the closure of the integers, then there is a sequence xn in this n that converges to x, right? So by definition, for every epsilon positive, I can find an integer n0, starting from which the distance between xn and its limit is less than epsilon. Okay? So in particular, what happens now? If I take n bigger than n0, then xn minus xn0, if I use the triangle inequality, I add and subtract x actually. This is less than epsilon, and this is less than epsilon. So xn minus xn0 is less than 2 epsilon, starting from n0. Of course, the n0 depends on epsilon. Now, if we take epsilon equal 1/2, then starting from a certain rank n0, this is equal just to 1 here. So I have xn minus xn0 is less than 1. So I have two integers now. Xn is an integer, and xn0 is another integer, and the distance between them is less than 1. So we have to conclude that they are equal, because if they were distinct, the distance between them would be at least 1. Okay, so what did we prove? We proved something remarkable, that a convergent sequence of integers is constant from a certain rank. Okay, so from a certain rank n0, all xn are equal to xn0. So the sequence is constant, and therefore the limit is this constant. So x, which is the limit, is equal to xn0. But this is an integer, so x is an integer. So I took an element x in the closure of the integers and proved that it is in the integers. So I have this inclusion, n bar is contained in n. But n is contained in the closure, so I have an equality. So what do we have? We have n bar equal n, so n is closed. Okay. So conclusion, the interior of n is empty, the closure of n is itself, so the boundary is also itself. Okay. Now for the second one, for z, the discussion is completely similar. So the interior of z is empty because z cannot contain a non-trivial interval. The closure of z is z because z is closed, same reasons. And therefore the boundary of z is z itself. For the third set, we already did them in the lectures. So the interior of Q is empty because Q cannot contain a non-empty interval. And the closure of Q is R. So we say that Q is dense. So therefore the boundary of Q is what now? Is R without the empty set, so it's R. Okay, fourth set, 1 over n. We have to find the interior, the closure, and the boundary. We already did half of them. So now, no interval, no non-trivial interval can be contained in A, actually. So no matter how epsilon is small, 1 over n minus epsilon, 1 over n plus epsilon cannot be contained totally in A. It contains element outside A. Actually, if epsilon is small enough, the intersection of this with A is just the singleton 1 over n. So otherwise stated, the points of 1 over n of A are actually isolated. Okay? And 0 is the only limit point of A. So the first observation is that, as we did for the integers, the interior of A is empty. And you already computed the closure. The closure is A union 0, so the boundary is also A union 0. That's it. Last set, the set of rational numbers whose square is less than 2, which is precisely the intersection of the rational numbers, the open interval minus infinity radical 2. Now, once again, since A is a subset of Q, there can be no non-trivial interval in A. So the interior of A is empty. Cannot find, because every open non-trivial interval contains irrational numbers, so it cannot be contained in Q. So the first observation is that the interior of A is empty. And I claim now that the closure is the closed interval minus infinity radical 2. This is, by the way, a closed set. Okay? I cannot close it in minus infinity because minus infinity is not a real number, but this interval is closed actually. We did that because the complement is open. Okay. So now I have to prove this claim. How do I prove that two sets are equal? Double inclusion. Okay. First inclusion. Minus infinity radical 2 is a closed set that contains A. But A bar is the smallest closed set containing A, therefore minus infinity radical 2 contains A bar. So we have a first inclusion. So this is contained in this. Now, for the converse, I take an element in this interval and I prove that it's an A bar. Okay, how do I prove that? I can use proposition 1.6. So take epsilon to be a positive number. The interval x minus epsilon x contains a rational number, right? Because this is not empty. Any non-empty interval, a non-trivial actually, contains a rational number y. So this number is less than x, so it's strictly less than radical 2. So actually y is where? Is an A. So what do I have? This interval meets A. So this bigger interval, x minus epsilon x plus, also meets A. So by proposition 1.6, x belongs to A bar. So I start from x here and prove that it's here. So this concludes the reversed inclusion. And that's it. So the boundary, since the interior is empty, the boundary is also equal to A bar. So the closure and the boundary are both equal to the closed interval minus infinity radical 2. And this concludes this video where we solve the first 6 exercises. In the next video, we will solve the remaining exercises. So thank you for your attention.